Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Rachel Starbuck from the Business Review, and I will be your host. It is our pleasure to have Arvia Technology with us today, who will be discussing Pharma Wastewater Solutions, the next era of trace-level organics removal. Today's guest speaker is Dr. Nigel Brown, who is the Founding Director at Arvia Technology. And I'd like to welcome you to our new webinar platform. You'll notice that this webinar is browser-based, so if you disconnect, please click on the link that you received via email to rejoin. You may move and resize the windows on your screen to customize your view. All of the icons along the bottom of your screen are the interactive widgets that we have on offer today, so please do interact with them all throughout the session. In order to ask questions, you can send them in via the Q&A widget at the bottom of your screen, or please use the top left-hand box. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. Please use the Help widget if you experience any technical difficulties or require any more assistance. So without further ado, please allow me to welcome Nigel.
Thank you very much, Rachel. Good afternoon, everyone. And as Rachel says, if you're outside Europe, good morning or good evening as applicable. Today, I'd like to talk about the removal of micropollutants with specific reference to the treatment of pharmaceutical effluents. I plan to start by discussing micropollutants, then looking at a new technology that we've developed that can remove and destroy these organic pollutants in water, and then compare this technology with current processes that are used for this application. I'll finish off with a number of case studies showing how the technology works. Micropollutants is a term that covers a wide range of substances, and there are a number of different terms that are used to cover specific compounds within this group. This includes things like POPs, persistent organic pollutants, emerging contaminants, PCPs, personal care products, red list substances, etc. All of these tend to be compounds that are present at low and trace levels, and are often new compounds with unknown or suspected detrimental effects on the environment. In general, these are not monitored, and these are often poorly treated with existing processes. From an industrial point of view, this presents a moving target as new chemicals are continually being developed and produced. There are improvements in analytical techniques that are detecting ever lower concentrations in the water, and our understanding of the effects that these compounds, both new and past pollutants, have in the environment is increasing. So a typical pollutant could include, for example, things like pharmaceutical products, pesticides, personal care products, flame retardants, hormones, nanoparticles, fragrances. There's quite a wide range. So I'm using the term micropollutants to refer to any of these compounds that are present at low and trace concentrations. Now, the main thing is that although over 70% of the surface of the planet is water, the availability of good quality fresh water is much more limited. And as time's going on, this availability of water is getting more difficult. Water scarcity and the need for security of water supply are becoming ever-increasing factors in considering the location of new industrial processes. In addition, there's increasing emphasis on treating water at source where the pollutant concentration is higher. This is rather than relying on the dilution of toxic substances within the sewer system. These factors are being driven by our ability to detect ever lower concentrations in the water, and also greater public concern over the long-term environmental and health effects of these compounds. These are driving legislation to reduce discharge consents, and this, as there is increasing evidence for climate change and population growth, this is likely to increase the pressure faced by industry. This is demonstrated by the fact that in the UK in 2009, 73 water treatment plants failed to achieve the drinking water pesticide standard for specific. In Switzerland, it's been determined that there's an average inlet concentration of 45 micrograms of micropollutants going into these wastewater treatment plants. And researchers demonstrated that existing processes will only tend to be effective against a certain number of these, and some are passing through the treatment plant without significant treatment. What this means is that there is now increasing pressure to improve the situation. Switzerland, for example, has now enacted legislation to manage micropollutant content at plant discharges. In the EU, more chemicals are being added to the priority list, and Denmark is currently exploring the possibility of introducing point-of-use treatment for sites with high pharmaceutical content. What this means is that new technologies are needed to address these challenges, and what I'd like to do next is go on and discuss a technology that we've developed here. But before I do that, there's a couple of questions I'd be grateful if you could answer on your screen regarding the level of expertise within the audience, so that I can try and pitch the content of this webinar correctly. So I'll hand back to Rachel to go through the questions with you.
Okay, thank you very much. So what is your level of knowledge of water treatment technology? And your answers are from very little, moderate, or advanced. So if you could please select the relevant answer to you and click on submit. I will just give you a couple more seconds to do so. Okay then, so if we move on to the next question. So what is your level of knowledge of the removal of organic micropollutants? And again, your answers are from either very little, moderate, or advanced. Again, I'll give you a few more seconds to do so, and please click submit. Okay then, so now if we move on to both of their results, I'll just hand back over to Nigel. Can you comment on these for me?
Okay, thank you very much, Rachel. So looking at that, it looks like that we've got some experts and some who don't know as much. So it's going to make it interesting to pitch towards. But what I would say is, if I do say anything that you would like further information about, please feel free to ask questions. And even if we don't get time to go through it in the question and answer session at the end, I will come back to you with a response. In terms of the second question, very similar sorts of response. So that's very useful for me. Thank you very much. Going on to the technology that we've been developing, this is a technology to remove and destroy low and trace levels of organic pollutants in water. What we've looked to try and do is combine the advantages of adsorption processes with those of oxidation processes. Adsorption processes are very good at achieving low discharge consents and concentrating the organics onto the surface. However, it is purely a concentration process. Once the adsorbent is fully loaded, then it must be disposed of. It can go to landfill or incineration with the ash to landfill, or it has to be regenerated. I'll talk a little bit more about the regeneration of granular activated carbon later, because Granular activated carbon is probably the most widely used adsorbent for industrial effluent treatments. But the other process that we look at is oxidation, and the benefit of oxidation is it is a destructive process. So that will destroy the recalcitrant organics, and we use an electrochemical process because this will do this on site at room temperatures and pressures. So the idea is that by combining the advantages of adsorption with electrochemical destruction gives us what we define as the ARVIA process, which is an energy efficient process for removal and destruction of low-level organics. So there are two key components of the ARVIA process. The first is the adsorbent material itself, which we've developed under the trade name Naiex. This material is a highly conducting carbon-based material, and this is used as an adsorbent within the process, concentrating the organics onto the surface of the adsorbent. However, because the adsorbent is highly conducting, we can then use that as the electrode within an electrochemical cell, passing an electric current through it. This oxidizes the organics on the surface to carbon dioxide and water, so we can achieve full destruction of the organics on the surface. The second key component of the ARVIA process is what we've called the ODC, the Organics Destruction Cell. The Organics Destruction Cell is basically a tank at the bottom of which sit a series of electrochemical cells. Between the electrodes of the electrochemical cell, a bed of Naiex is inserted. Effluent to be treated is then fed into the tank, and this then percolates down through the bed, which is where we get adsorption occurring. This is very similar to conventional methods of treating water using granular activated carbon. The treated water passes through the system, and then we can pass an electric current through that. That oxidizes the adsorbed organics, producing carbon dioxide and trace amounts of carbon monoxide and a little bit of chlorine if there's chloride present. But also, because we're doing oxidation, we also have to correspondingly do reduction, and we reduce water to hydroxide ions and hydrogen. Both of those can vent safely to atmosphere. So the key points that I want to get across in this is that we can use the Naiex to adsorb and concentrate the organics, and that means that we then get efficient electrochemical oxidation. But the way we've designed the cell is such that we can do continuous and simultaneous adsorption and electrochemical regeneration within a single unit. And we believe that this is the first time that this has been achieved. Now, what we're looking to target with this process is those waste streams containing low and trace levels of organics within the water. So these are particularly things like emerging chemicals, micropollutants, endocrine disruptors, pharmaceutical products, toxic, hazardous, non-biodegradable chemicals, tertiary organic polishing, and also destruction of microorganisms, which is an aspect I'll touch on again later in the presentation. So the technology itself produces a treatment to destroy low-level organics. It will also destroy microorganisms, and it can provide residual chlorination if there's chloride present. Hence, this gives a stable water that can be stored and reused back into the process in a single treatment step. It will give a strong ROI, rate of return on investment, because there are no chemicals used within the process. The high conductivity of the NIEX means that we don't need to add any chemicals to provide conductivity in the water. We can do that purely through the NIEX. I've put down there we produce no secondary waste. As you will see from that earlier slide, we do produce some carbon dioxide and some hydrogen. However, these are at levels that are very low, and all we do is vent those direct to atmosphere without any problems. The next point is one that I think is particularly important for the technology. The energy consumption that we use is proportional to the organic concentration. If you look at the adsorption isotherm on the right, what this basically shows is that as the concentration in the liquid phase gets lower and lower, the amount of organic that will load onto an adsorbent also gets smaller. What this means for adsorbents like activated carbon is that when you're treating low concentrations in the liquid phase, the amount on the solid is low. But when you send that off for regeneration, it's still the same cost as it would be if you'd treated something at high concentration. So the cost of regeneration remains constant. With the ARVIA process, the amount of energy we need to put in to destroy the organics is proportional to the organic load that's on the surface of the NIEX. Hence, if we're treating low and trace levels, the amount of energy we need to get in is very low. Hence, I think that's a key thought that I would like to leave you thinking about. The second point I want to emphasize is that the adsorbent NIEX is reused within the process. So this adsorbent will keep going hundreds and thousands of times without any problem. And in fact, to date, we don't know quite how long it will last because we haven't run a process for the years that are needed to find out if there is a cut-off period when it will fail. But it is looking as if it will last years in the process. So finally, just to say, this is a treatment solution that we would envisage often being used on a site. It can be mobile, skid-mounted, containerized, and it can be retrofitted into existing plant or processes. So at this stage, before we go on to comparing the process that we're looking at using with other processes that may be used, it'll be interesting to find out what other processes you're currently using in the to treat pharmaceutical wastewater. So I'll hand back to Rachel, who will take you through the next poll question.
Okay, thank you very much, Nigel. So your next poll question is, do you use any of the following to treat pharmaceutical wastewater? And please select all of the relevant answers that apply. So your answers are from ultraviolet, biological processes, granular activated carbon, advanced oxidation, membranes, ozonation, incineration, discharge to sewer, or not applicable. So again, please select all of the relevant answers and click on Submit. You may need to resize your window and scroll down to see all of the answers and the Submit button. And I would give you a couple more seconds to choose your answers. Okay then, so if we move on to the results. Okay, so Nigel, can you please comment on these results for me?
Yep, I certainly will. It's very interesting that with the exception of ozonation, there's quite a wide range of processes currently being used for the treatment of these wastes. Interesting to see that biological processes are being used, and membranes are somewhat higher than I would have expected, along with more on incineration than what I have expected. So that's quite interesting for us to know. And hopefully as we go and compare the processes, in the next 2 or 3 slides, we'll get a feel for how our process compares with those. In terms of competing technologies, there's basically 2 approaches that are used in the treatment of pharmaceutical wastewaters. The first is we can use techniques that destroy the organic, and these are nearly always oxidation processes. This can be either chemical oxidation, biological oxidation, advanced oxidation processes, but key to it is we're relying on oxidation to destroy the organic. The second approach is to try and concentrate the amount of organic into a smaller volume. And this is traditionally the effect that's used by granular activated carbon, where with granular activated carbon you concentrate the organic onto the surface of a solid, which can then be disposed of or treated in some way. The other approach that's taken is again a concentration process, and that's looking to use membranes in things like microfiltration, reverse osmosis, ultrafiltration. And the idea there is you filter out those impurities in the water to produce water, but you then produce a concentration stream. So looking at those 2 types of process in more detail and comparing the technologies, you can really see that if we're doing oxidation, the key things that happen is you tend to produce byproducts. And this is true if you're using almost any oxidation process. However, the interesting thing is that by absorbing the organic onto the electrode first and then passing an electric current to it, we can actually fully oxidize the adsorbed organics without producing any breakdown products. So that's quite a fundamental difference between our oxidation technology and the other oxidation processes that are there. The other key thing that is shown by this is obviously that concentration processes don't produce byproducts. So granular activated carbon, when you use it, doesn't produce a byproduct, and membrane processes don't. But the big problem is you still have a waste stream to deal with. So with the activated carbon, we will have the solid activated carbon, which needs to be disposed of. With ultrafiltration or reverse osmosis, we will have a concentrate stream that we need to treat. In terms of the footprint of the plant, because we're treating low concentrations of organics in the water, if you're using chemicals, it's very difficult to ensure that you get full contact between the oxidizing chemicals and the polluting chemicals. And to get the oxidation to occur, these have to come together to react. So you tend to rely on having relatively large residence times. Typically 1 to 2 hours are quite likely to ensure that we have sufficient time for the reactions to occur, which obviously gives large-scale plant. In terms of GAC, that can be a smaller footprint, but GAC isn't always effective. And the other key thing that we have to is that you still need to do something with that waste-loaded activated carbon. It can go for regeneration, but if you use regeneration industrially, it'll be a thermal process, and that results in the loss of 10 to 15% of the activated carbon to oxidation and attrition. And obviously, because you're using a high temperature process, it's a high energy, high cost process. In terms of membrane processes, again, they have low footprints, but membrane processes traditionally are both expensive in capital operating terms, and you still need to do with something with the waste stream that is produced. The RVIA process gives us the benefits of the 2 types of approach: concentration and oxidation. By using the adsorbent, we get a short residence time in the system, giving us a small footprint. but it's also a simple process, can operate unattended 24/7, and it's cost effective over a wide range of different types of pollutants. So going on from there, obviously one of the key things is what will be the cost of treatment using the ARVIA process. So what we've tried to do is assess what the CapEx and OpEx cost of this process would be treating compared with other treatment technologies. The data from this graph is from two sources. The colours in blue are from an UCWER report. That's a report from the United Kingdom Water Industry Research Body, who did a report a few years ago on the treatment of these chemicals in a treatment plant, and they estimated what the costs of those plants would be. We have taken that basis and designed an ARVIA treatment plant which would do the same job, and estimated the CapEx and OpEx of the system. So as you can see from that graph, it is the process is cost effective in terms of both its CapEx and its OpEx. So what we were doing with this is the ARVIA system is very much a modular system. Scale up is relatively easy through increasing the number of modules that are there within the system. So we currently have two module sizes available. And the second is the ARVIA ODC 10100. As you can see from our naming convention, the last letter of that is the electrode size, and the first letter is the number of electrodes that we have within a module. We can then define how many of those modules we fit together to treat the flow rate and the organic concentration that is present in the water. So scale up is relatively easy for us to achieve. So looking at the capabilities of these two units, the ODC 450 is designed to run at flow rates of up to a cubic meter an hour, destroying 70 grams of organic. It's a potentially mobile, and it is a modular unit. And in terms of size, it's 60 centimeters by 30 centimeters in terms of its footprint. The ODC 10100 is about 10 times the size, giving us a flow rate of 10 cubic meters per hour, treating up to 0.7 kilograms of organics per hour. And again, it's a modular system, and it has a footprint size of just over a meter square. So at this stage, before we go into the case studies, what I'd like to do is find out what the challenges are in terms of the current water treatment processes that you use, and what would be the sort of factors that would affect your decision in terms of investing in new technologies. So again, I'll hand back to Rachel and ask her if she can go through those questions.
Thank you very much, Nigel. So yes, as Nigel said, just before we go on to the case studies, I'll just ask the next two questions. So which of these challenges is most significant to your water treatment process? And again, you can please select all that apply to you. So we have regulations, treating emerging contaminants, water scarcity, pressure to operate sustainably, cost of water disposal, or not applicable. So please select your relevant answers and click submit. Okay, so I'm now going to move on to the next question. And which of the following would most affect your decision when investing in new technology? And again, please select all that apply. So we have footprint, management of byproducts, operating cost, ability to treat a wide range of chemicals, environmental impact, corporate social responsibility, or again, not applicable. So again, please select all of the relevant answers and click on submit. I'll give you a couple more seconds to do so. Okay then, so if we move on to the results. So for the first question, Nigel, can you comment on this one for me? Nigel, can you comment on these answers for me?
Oh, sorry about that. I pressed mute by mistake. In terms of the answers, very interesting that water scarcity still isn't quite as big a problem as I expected. But yes, it is being driven by regulation and emerging contaminants and the need to demonstrate sustainable operation. So that's a very interesting finding. In terms of the factors that would affect decision, the ability to treat chemicals, yes, is very important. Operating cost, yes, and environmental impact are high on the list there. So that's a very useful slide for us, and hopefully I'll be able to address some of those as we go through the specific case studies now. So going on to the case studies, what we've tried to do here is present a few cases of or micropollutants that we've been treating here at Arvia. The first one is a range of pharmaceutical components, micropollutants, which we used in a treatment process where we did a once-through process, just going straight through the unit, looking to see whether we could remove those. And the objective of this was really to show that we could remove these persistent pollutants during continuous operation of the process. So if we look at the results of that, as you can see, using this with a 3.6-minute residence time in the cell, we were able to remove typically between 80 and 100% of the pharmaceuticals that were present in the water. So this was an unoptimized study. It was just a once through. So that's a very, from our point of view, very exciting result. The second case study involved triclosan, which is an antibacterial and antifungal agent found in a range of products. And although it's being increasingly removed from these products, it is persistent in the environment and it is still found in the environment. So what we were hoping to do with this was demonstrate removal and oxidation of the triclosan and estimate what the cost could be for removal of this compound from water. Hence, this particular test was done using a recirculating system, feeding out of a holding tank and then back into a holding tank, which is why you see the gradual reduction in the amount of triclosan in the holding tank. We used high concentrations of organic within the mix to ensure that the adsorbent was fully loaded, so that we were able to demonstrate that by passing the electric current through it, we could continue to remove the organic from the waste. And as you can see, after 10 hours, we respiked the solution with some more triclosan, and again, we were able to keep removing the organic, the water. We also looked to see if we could get lower than that, and we removed down to 100 parts per billion, but that wasn't a specific requirement of this project. And the treatment cost, we estimated that we were going to put in around 25 to 47 kilowatt hours per kilogram of COD that was removed from the effluent. So continuing on to a different type of study, this was based on a real effluent that was provided by a company that is working in a water-stressed region, and they are now being forced to consider zero liquid discharge to recycle the water back into the process. They have on site an existing biological treatment process, but some of the pollutants going in are non-biodegradable, and so obviously before that water can be recycled back into the process, these must be removed. So what the objectives of this particular project were to remove that COD that was non-biodegradable, turned out to be around 400 milligrams per litre, and we had a target to hit of less than 50 milligrams per litre of COD. This was water that had already passed through the biological treatment plant, so we knew that most of the pollutants present were non-biodegradable. We also estimated what the cost would be for this process. So in terms of the results, I think the picture on the left, as they say, a picture paints 1,000 words. Yes, we were very successful in removing the colour and the organics, and we got below the 50 milligrams per litre target that we had been given. We also demonstrated that the NIEX after treatment was the same. The absorptive capacity was the same as the NIEX, as fresh NIEX, and we estimated that the amount of energy we needed to be put in was the order of 20 kilowatt hours per cubic meter of effluent treated. So that was a real effluent. This next one is also a real effluent, and this is a hospital waste. And we're working with a company who does high temperature incineration. They take these hospital wastes to incinerate, but obviously incineration of water is a high cost, high energy process. And the company concerned was looking for alternative methods to dispose of these waste materials. We received a number of samples from them where we were required to remove at least 95% of the incoming COD and to estimate what the amount of energy would be needed to remove and destroy the organics present. So on these, we got three wastes with very different CODs coming in. And with all of them, we were able to achieve greater than the 95% target that we had been given. In terms of the energy required, this is one of the things that is very interesting from this slide, is that typically we needed to put in around 30 kilowatt hours per kilogram of COD removed. And this was the same whether we were having an organic load of 880 milligrams per litre or an organic load of 26,000 milligrams per litre. And this is just to reinforce the point I made earlier, that it's not that our cost, regeneration cost, is very much tied to the organic load rather than the amount of liquid that's there. It's the amount of organic that we have to destroy that is key. And that typically works out at around about the 20 to 30 kilowatt hours per kilogram of COD. The ROI in this case was calculated to be significantly less than a 12-month period. So the final case study I wanted to bring in was metaldehyde. This is a pesticide that is actually used to control slugs and snails. It ends up in water, and when this water passes through drinking water treatments, it is not removed very effectively. Hence, in the UK, some treatment plants are failing to meet the quality limit of 0.1 parts per billion of metaldehyde. In the UK, the DWI, the UK Drinking Water Inspectorate, has said that the water utilities need to find a solution for this by the end of 2015, and they are currently working with us to see whether or not the RVIA process will be a solution for this. Key to this one is the fact that we now need to be working at the sub parts per billion level, which obviously is an area where most processes find it very difficult. So the key things that we were trying to do with this process was to demonstrate that we could remove metaldehyde from a sub parts per billion level down to below 0.1 part per billion, and to estimate what the cost of treatment would be for that process. So in terms of the results, the great thing from our point of view is that over the period of the trial, none of the samples were above the 0.1 part per billion level. The amount of energy that we put in was 0.5 kilowatt hours per cubic meter, but this is way in excess of what we think we'll be able to achieve with some optimization. And in terms of the process, we were operating with residence time of the order of 1.5 to 2 minutes. So the process itself was working very effectively. So the final thing that I would like to come on to is one that is slightly different, but I feel is worth highlighting as a potential benefit of this process, and that is the fact that as well as absorbing micropollutants, the process is also effective at absorbing microorganisms. So we've tested this against a range of different microorganisms: E. coli, Pseudomonas, fungal spores, Legionella bacteria, algae, and what we've been able to demonstrate is that we can absorb all these microorganisms onto the surface. When we pass an electric current through these species, we can then kill them, disinfecting the water. And in a continuous trial that we did, we achieved an 8.5 log reduction in the number of colony forming units that we used. Whilst this work is at a slightly earlier stage, the data that we're getting is really exciting, and this ability to be able to remove both organics and disinfect within a single process, plus the ability to produce some residual chlorination to provide a stable matrix after treatment, gives us, I think, a very powerful process for treating a wide range of wastes containing low and trace levels of organic pollutants. So finally, if I may summarize what we've just been talking about over the last 3/4 of an hour, I think it's fundamental to say that the landscape for water use and wastewater treatment is changing. It has been said that if the 20th century was the century of oil, the 21st century will be the century of water. As we find increasingly trace levels of organics within water, there's going to be increased pressure to do something about that, and existing technologies are not able to effectively and cost effectively remove these down to the levels that are now being required. Arvia has developed a technology specifically to do that, combining the best of the concentration process with the best of the oxidation process, which gives us a range of benefits without any of the disadvantages of the existing processes. So Arvia's ODC unit will remove and destroy those contaminants within the water. We can do this without adding any additives to the water, so we don't need any chemical additions. We don't produce any byproducts from the process, and there are no waste streams. the fact that all we're doing is removing organics and not adding anything to water means that it will make water recycle and water reuse much more effective. The system is designed so that it's a single unit where we achieve both absorption and regeneration, operating continuously. It's got no moving parts, low maintenance, and can operate unattended 24/7. We believe that this offers a cost-effective solution for treating microorganics and particularly pharmaceutical products in water. So at this stage, I'll hand back to Rachel, who has been receiving questions from you, and I will attempt to answer those questions that have come through. And if you do have any further questions, please do feel free to keep those questions coming in. And if I don't answer them now, if there's no time available, I will come back to you over the next couple of days with responses to those questions. So, Rachel, if I may hand back to you.
Yes, thank you very much, Nigel. So yes, thank you to everyone who has already sent their questions in. Please continue to send in your questions via the Q&A widget at the bottom of your screen or using the top left-hand box. So as Nigel said, we will get through as many of the questions as possible. However, if we do not have time to answer them all in this webinar, then Nigel will get back to you at a later date. So for your first question, Nigel, have you ever used electrochemical oxidation for olive mill waste water treatment?
Ooh, interesting application. It's not one we've yet tested. It's a troublesome waste, I know. In terms of treating that, there is no reason at all why we aren't able to treat that. I think the main question would be the concentration of organic that it's coming in at. If I remember olive oil waste waters, they tend to be quite high in organic concentration, and there's probably a degree of biodegradable material there. So it might be that what we would need to do would be to look at a combination of processes. The first one to achieve bulk removal of some of the organic, and then to use the ARVIA process as a polishing stage at the end of it to remove any organics that are still remaining. I think that is likely to be a better treatment route rather than trying to rely purely on an ARVIA unit to take out all the organics. In terms of cost, a pre-treatment for bulk organics removal and a polishing of the ARVIA system, I think would be the best option there.
Okay, thank you very much. And how do you regenerate Naexx?
How do you regenerate Naexx? The Naexx is in the form of a bed between two electrodes, and we pass an electric current through that. The oxidizing conditions we get within the anodic compartment of the electrochemical cell are very strong because we're getting oxidation at the surface of the Naexx. This is because the Naexx operates as the electrode. What we've been able to show is that we can achieve full mineralization of the adsorbed organics without producing any of the breakdown products that you would normally get with electrochemical processes. And a key thing that I would just follow on from that is often if you use electrochemical oxidation water, what you will also do is oxidize the chloride to chlorine. The chlorine will then react with the organic that's present, producing a chlorinated organic, which tend to be more toxic than the starting material. In the case of the ARVIA process, the fact that we've absorbed the organic means that we don't form chlorinated organics in the water, even if we have chloride present.
Thank you very much. And is it possible to use ARVIA technology as a pre-treatment of biological process, or is it better to use it as polishing?
Again, that's a very interesting question. One of the benefits that we've shown with the ARVIA process is that we can achieve preferential removal of certain compounds from water, and these tend to be the chlorinated toxic organics. What that actually means is, yes, we can use it as a pre-treatment process to remove those toxic chemicals from the water, and that water can then go on for cheaper biological treatment because those toxic chemicals have been removed. It is a point that I didn't actually bring out in the presentation, which I think is worth me making now. Because of the way the process works, we can actually control the amount of organic that we remove from the liquid phase. So in this particular case, if we wanted to stop treatment with just the removal of the toxic organics, we can do that by controlling the amount of regeneration current we put through the process. It's not a case of we have to remove everything. We can control the amount of the organic that we take out of the process. However, having said that, again, it can be used as a polishing process, and my gut feel would be in a large number of cases, a polishing process is the best way to use this, but there will be specific examples where pre-treatment is a good idea.
Thank you very much, Nigel. And have you already tested ARVIA technology on wastewater charged with gelatin?
No. I can't see it being a problem. I think it's one that we will be able to remove effectively from the process, but it's not one that we have yet tested. So if someone does have an interest in that, please feel free to contact us separately, and we can certainly look at trying to remove that from the water. I see no reason why we can't.
Okay, thank you. And I hope I pronounced this question correctly. So how can I apply electrochemical oxidation to a point of use technology involving hybrid clay and Plantago ovata husk?
That's a very interesting. You pronounce that very well, if I may say so. I don't think I would have stood a chance on pronouncing that particular one. If there's presumably by the fact that there's husks present, obviously that's a solid material. The one thing we don't really like to put into our system is solids. As you can imagine, the process works with a bed of material, and if there's solid present, the system will filter that out. Whilst this can be very beneficial if it's a low level of solid coming into the system, it means that the water coming out doesn't contain that solid. It does mean that we have to back flush the system more often to remove the solid from it. So preferentially we would take out the husks using a different process upstream, and then pass the water without the husks into our process. So that would be my preferred way of doing it. Again, you know, if I've not been clear on that particular question, please feel free to contact me separately.
Thank you very much. And you also mentioned only COD. What about N or P or AOX, etc. after treatment?
After treatment. So in terms of inorganic species within the liquid, they will generally pass through without treatment. So if they're present in the water, you know, N and P species that are present in the water, then they will tend to pass through the process without treatment. So we will typically look at those passing through without any treatment. In terms of if they are present within the organic, so if we've got chlorine associated with the organic, or a sulfur species, or a nitrogen, then what we will do is oxidize those species, and they will end up as an inorganic oxidized species within the water phase. I hope I've answered the question that he was specifically asking. Again, I can follow up separately if there are any further information needed.
Thank you. And can the NIAX process be implemented for the treatment of dyes such as methylene blue and Congo red?
Yes. That is one of the areas that we've looked at, is the removal of particularly organic dyes and things. Those are ones that I think we've actually specifically treated, although I would have to check my records to be sure, but we would have no problem in treating those.
Nigel, it seems your phone has broken up. I'm just going to try and get you back on the line. Please just bear with us a couple more minutes before we get Nigel back on the phone. Okay, so Nigel is just dialing back in. Please just bear with us one more minute.
Hello, Rachel.
Hello, Nigel. Welcome back.
I'm sorry about that. Both our lines died at the same time.
Oh, dear. Okay. Well, do you want to carry on finishing off this question? Shall I ask it again?
Please ask it again, because I may have missed it, so I'm not sure when we got cut off.
Okay, so can the NIAX process implemented for the treatment of dyes such as methylene blue and Congo red?
Fortunately, that's the easy question, in that the answer is yes. A lot of our original work was done on dye systems, and we have treated, I think we've actually specifically treated those two compounds, although I'd have to check the records. But yeah, I am confident that we would be able to remove the colour from those particular, caused by those particular dyes.
Okay, thank you very much. And as a new technology, have you considered European funding?
Again, that's an interesting question. It is an area we are currently actively looking at. We're working with one of the water companies on a project under Horizon 2020, a collaborative project. But for this group, we're actually looking at putting in a separate application to look at pharmaceutical waters. We're working with another company on that, and we will be looking for potential collaborators. So if anyone within the pharmaceutical industry thinks it would be interesting to work with us on a European funded project, then we are looking for a suitable pharmaceutical partner to work with on that. So timing is quite good for that particular question.
Okay, thank you very much. And which chemicals do you use to aid oxidation?
We don't use any chemicals within the process. What we rely on is oxidation within the anodic compartment where we have the organic and the water. We don't specifically add anything to it, so we don't need to add any chemicals. One of the main benefits of this process is that we don't need any chemical addition to it. It purely relies on oxidation within the anodic compartment to achieve oxidation of the organics.
Okay, thank you very much. And I think we have time for one more question. So in one of your slides, you referenced the existence of a vent that comes out from the system or cell. So will it be required a VOC treatment for the vent?
No, what we've shown is that we've analysed the off gases coming off, and we don't produce any volatile organics. So as far as that's concerned, no. All we do with the waste gases is we basically vent direct to atmosphere with no additional treatment required.
Okay, so thank you very much. We also have had quite a few people asking if they can receive the presentation by email. So just so you're aware, you will receive the on-demand version, a link to the on-demand version in a couple of hours, so you can watch that at any point at your own convenience. Nigel, do you have anything else to add before I conclude?
No. I hope, all I can say is I hope everyone's found it interesting. I hope they found it informative, and if they do have any further questions, please feel free to come back either to myself, Charlotte, or info at Avia Technology, and we'll do our best to answer the questions.
Okay, thank you very much. So sadly, that is all we have time for in today's session. So as we said earlier, if you didn't get round to answering your question, then Nigel will get back to you at a later date because we have had a lot of questions in. So that just leaves me to thank Nigel for what was a great presentation, and thanks to Avia Technology for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. The Avia technology is truly groundbreaking and represents a major advancement of overcurrent advanced oxidation processes that can treat and trace low-level organics. Treatment problems that are currently insoluble can now be solved in a cost-effective and safe way. If you have any additional questions on the technology or would like some further information, then please get in contact directly using the contact details on your screen now. So we look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BR Webinars for daily updates, and join our LinkedIn group, Business Review Webinars. So thank you once again to everyone, and I hope you all have a nice day.